So important thing is that the history I will show later. So we just perturb the metric mu nu, g mu nu, 0 plus h my node is h mu nu. And then this one is the Schwarzschild metric. Okay. And then the Ricci scalar is also like this way. Sorry, the other one. Delta R mu nu. And then, so we just want to solve the vacuum equation. Vacuum Einstein equation. Equation R mu nu equal to 0. So this means that since the delta, this should be 0, since the R mu nu 0 should be 0. So the Schwarzschild metric will satisfy this condition. Okay, so that's the case. And then, so we want to solve this equation by perturbation theory. And to do that, we will do the spherical harmonics. Let's see, so the tensor, if you have a tensor, so this one is really actually, there is a huge theory about so it's, if you search in the Google or whatever, scalar vector, I will show you later, and tensor perturbation. There's a huge literature will show up actually. And I will show you later. And there's a mathematical file and so on. LM and Axel mu nu plus, so L and M. Sorry, this should be A and the plus sum of LM, B LM, B polarization, and the LM, and mu nu. Okay, so you just do the, so these are tensor version. So these are tensor version of the spherical harmonics. Like this way. Okay, so then, so axial and polarization means that if you have a parity transformation to this FLM, theta and phi mu nu to the F tilde LM pi minus theta, so pi minus theta, and then pi plus phi, and this is equal to minus 1 to the L plus 1, L plus 1, L or L plus 1, F mu nu, like FLM, like this way, like this way. So if this is a case, this is called axial, odd, and then minus 1 to the L FLM is polar, or like this is called even. So this is the perturbation theory, and then so we want to derive that so the odd case is easier, and this is called axial. So this is called Ricci equation, and the even case, the polar case is called the Rayleigh equation. So just coming from here, So this equation is called the Rayleigh equation. So this is found by 1958. This is 1970. It turns out that okay, I will just write down the equation. Derivation I will show you in the slides. I will show you in the slides later. Also, I just put it into the derivation, channel circle derivation in the lecture note, in my lecture note, which I wrote the last time on the blackboard, but it looks horrible. But now I'm not going to repeat. So important thing is that the, let's see, okay, maybe just write down the equation is better at this moment. I will show you in the slide later. So equation is that so this equation become like this way, dr star square plus, okay. Which one I should show you? Okay, maybe I can show you this equation, plus omega square minus b plus minus. So this acts on psi plus minus equal to 0. So it's really like a Schrödinger equation of the quantum mechanics. This R star is the tortoise coordinate. Okay. And omega is actually, we assume that it's psi plus minus. So the plus corresponding to this guy, the minus is corresponding to this guy. I don't know why. This is somehow notation. Anyway, so that's the notation. Here, this guy is the potential. Is a very simple form for Redjet Wheeler, but the Derrida equation is somewhat complicated. But I will write down later. But the important thing is that so if you solve this equation, we can solve by WKB and so on by analytically, WKB approximately, WKB. But nowadays there are lots of methods. So others is numerical, and also nowadays actually string theory is even like they analytically exactly. There is a way to do that. You can do that to solve this equation. And it turns out that the following thing happens. So let's first write down the equation. The B plus is something like 1 minus 2m over r. And the last time I wrote it like this way, over r squared minus 6m over r cubed. So this is the Redjet Wheeler case. B minus is kind of complicated. Let me write down at least the form. Okay, so the same factor. It's kind of complicated. Okay, it's a rational function of r. So the r cubed, qr plus 3n squared, and then there are lots of factors up here. Anyway, so that's, derivation is complicated. I can show you later. Q squared and r squared plus 18qm square r plus 18m cubed. So that's the function. So this is the Derrida case. Anyway, so here the potential look like this way. B plus minus roughly this is 2m as a horizon. And then here we assume that the spike will show up like this way. Maybe it's too much. Okay, anyway, so that's spike will be around 3.3m roughly. Both are like this way. And then here you have the horizon, and then you have an infinity. So the boundary condition you have to impose is that, of course, in black hole, nobody can escape from the horizon. So that it has to be ingoing. In the horizon, ingoing, so that if e to the I omega t minus r star, something like this one. I don't remember the detail. I don't know which one is the ingoing notation in my notation. In my notation, it should be somehow plus, and then in here is at the infinity. So this is So this is ingoing at horizon. Horizon is the R star goes to. So at the horizon, what is the value of a tortoise coordinate? What is the value of tortoise coordinate at the horizon?
Infinity.
Minus infinity. And then, so the R star goes to infinity, that's the phi infinity, this is e to the I omega t minus R star. So this is the boundary condition we have to, this is outgoing at the infinity. Outgoing. Okay, so that's the boundary condition. And we have to solve the equation by using this boundary condition. The important thing is that so this is what these people found is that so important thing is that they found that roughly they behave like a psi plus minus is both behave like a e to the I omega n t plus t minus r star when r star goes to infinity, and this omega n is a discrete somehow, discrete, complex and discrete, complex, discrete, discrete, complex body, so that the omega n is something like omega n real plus I omega n imaginary. So this is the form. So n runs for 0, 1, 2, dot, dot, dot. So so the complex mean that the wave function is damped wave function. So therefore, as the so this will decay. So they're how to say? If you go to the infinity or as time goes by, so the amplitude of the wave function becomes smaller and smaller. Okay, so that's the ring down phenomenon. Ring down.
If the imaginary part is positive, right?
Yes.
If it is negative, it won't.
That's true. But it's hard to believe. I mean, once something is scattered, it's the increase. It's hard to imagine. So you have to, So you have to, once you solve this is positive, you will see. And so that's why it's called that's why it's called quasi normal mode. So this is called quasi normal mode. Normal mode is just a usual oscillation. Quasi means you have some damped factor because due to the imaginary part. So that's why it's decay as the time passed. So what's really happening is that if you do the perturbation theory, so there's time, and then here you have a radius, and there is some potential wall is around here. Potential wall is around here. So therefore, around this is 2m, say 5m or something like that. Around here you have a some potential wall, roughly speaking, is around here. Big potential here, and if you just some perturbation occurs from at some point, some will just enter like this way, or due to the potential wall, it was scattered like this way at some point, and then there's sometimes there is something going on in the middle, so there's this kind of phenomenon will happen. Okay. So those are what's going to physically happen. So if there's a perturbation initially happen, there is scattering occurs, there is scattered outgoing, scattered. But some part of the perturbation will just penetrate this potential wall and then go into the black hole horizon. Okay, and then since due to the ring down phenomena, one can show that black hole is the stable under perturbation. That's the so around 70s people just found, and moreover, what's important is that they both has this odd and the polar part has this kind of like a discrete complex value. How to say? The spectrum, but Chandrasekhar and the collaborator found that they are related. It's called iso spectrum. Mean that it has both the same iso spectrum. So this is Chandrasekhar. In 1975, around 1975, I don't remember the precise date year. Isospectrum means that they both has the same frequency. So even like a B plus, not psi. Isospectrum means that psi plus minus has the same frequency spectrum. Okay. So somehow they have a different potential, as I wrote. The B plus and B minus have a different potential, but somehow they have the same omega n. Okay. So that's the what's really happening. Is that and then this can be shown as follows. In fact, if you look at this one, I will erase maybe. Okay, I can erase here. So what the Chandrasekhar found is that this B plus minus is related to like this way: f square plus minus df dr star minus 4 lambda square lambda plus 1 square divided by 9 rg square. Okay. So B plus minus is just can be written by single function capital F, and this capital F is called superpotential. I realize. So this is called superpotential in this community, but it has nothing to do with supersymmetry. There is a terminology superpotential in the supersymmetric community, but it's a different. It's called superpotential, and this F can be written in explicit function. So this F is equal to 3Rg. Of course, Rg is 2n. So just Schwarzschild radius. Rg minus R divided by R squared 2 lambda R plus 3Rg minus 2 lambda plus Rg. Somehow, if the potential is related to this the single function f, capital F. One can just show that thing.
What is lambda?
Huh?
What is lambda?
What is lambda? Sorry. This should be L. Sorry. This should be L. And Q, sorry, good question. This should be L. So L here and the Q should be function of L. I think I skipped many details. Q is equal to L minus 1, L plus L minus 2. L plus 2 divided by 2 here, and here is L. Sorry, L. Thank you very much. L, and this is L, and then L. Good. Thank you very much. So they are related by a single function. It's called superpotential.
Okay, this is R star, right? In the definition of F, superpotential.
Yes, yes.
R star.
Huh?
R is R star, or because you are taking derivative with respect to R star.
Yes, yes. It should be R star. It should be R star. I don't. Most likely it's okay. R is okay. Because I mean here, B of plus is also a function of R, right?
Okay.
So but it makes sense, right? I mean, the relation between dr, I think dr star is equal to 1 minus 2m over r divided by like this, right? Am I correct? I think this one you should remember before you finish this lecture. Yeah, let's do computation. Okay. So R star is equal to R plus 2m log R to m minus 1, right? And dr star is equal to dr 1 plus R over 2m minus 1 divided by dr. Is that okay? Do you agree with me? Sorry, 1. Okay. So then, therefore, so this should be equal to what? R minus 2m, R minus 2m plus 2m, right? So therefore, this is R, right? Okay, so therefore, it's opposite, like this one. Okay. Okay, is that okay? Is it okay? I hope I'm not I don't make a mistake. It should be okay, right?
Yeah.
Yeah. Fine. So it should be function R. So it's okay to write down the inverse of R. So those are the what Chandrasekhar found. Okay. And then let me briefly show how does this WKB approximation will work. Okay. So let me briefly show WKB approximation for this equation. So we want to apply, this is WKB approximation onto this equation, and then solve why this spectrum is discrete. That's what I'm going to show from now. And after that, I will move on to these slides. Okay. Move on to the slides. Okay, so let's do the WKB approximation. So what is WKB? approximation. So what we are going to do is something like a b plus minus r, and then here is r, and this is 2m, like this way. And then, so here is around r max, or r max. Let's go r max. And then omega is something like omega is around here. So value of omega is something like where's? It's very close to the. So this is omega. So that the difference between them is very tiny. Okay, and then here. Did I call it this one? Is the okay R so I call it R0. R0. Okay, R0. And then here you have the this point is this point. If you plot this point is I call it R1, and then this point is I call it R2. Okay, and this region people just call it somehow matching region. Matching region. Okay, so that's the situation we consider. Then if you try to solve this equation, so I approximate this one is equal to q plus minus of x. And I don't care about the plus minus sign from now on. So the equation we are going to solve is that there's something like d square of psi of d square r star plus q r star is equal to psi equal to 0. So here, even though that I wrote the b plus minus as a function of r, it's free to change from r to r star. Then of course the change of function will change, but I just write down such a function as a q or r star. Okay, and then. So what's really happened WKB equation tells us that I call it this one region is something like I call it this region is 1 or so. Yeah, 1. And this region is like as far as I remember is 3. Okay. No, sorry, the other one. Okay, 1 and 3. And in the matching region is 2, and then WKB approximation would WKB tells us the wave function should behave like this way. In the q to the minus 1/4 and exponential, and then integral plus minus I integral over x2 over x, and then okay, I don't want to write down r star 2 and so on. So let me call it x at this moment. So then q of x 1/2 square root dx. So this is the what you learn in quantum mechanics, and then psi. And number 3 is q to the minus 1/4 exponential plus minus I. The x1 q of x square root dx. So that's the form of WKB wave function around the 1 and 3 region.
Approximation is approximate solution of that equation, right?
Yes, this equation. Yes.
What is their assumption? What is the approximation?
Okay, I will tell you. Yeah, I will tell you. So let's recall what's WKB. So recall WKB. So I will explain this one just a moment. So this WKB, okay, review of WKB. Okay, WKB, which is something like this one. So the H bar square. So the Schrodinger equation is something like this one. Psi. So this is Schrodinger equation. Schrodinger equation. Okay, and then to solve this equation, so we assume the assumption is wave function is something like this one. 1 over h bar, sum of n, h bar, n Sn of x. Okay, n is 0 to infinity. So that's our assumption. And plug this one into here. Okay, plug into this one into here. So the psi double prime of x is around roughly equal to, I mean, you just do the derivative. Sum over Sn prime square plus 1 over h bar, sorry, not epsilon, h bar, sum n, n, Sn double n, okay, and then something, the same thing happened here. The same factor is here, double. Okay, and plug this one into ODE, and you just compare h bar order by order. H bar, oh, so this one I cannot erase. So plug this one, this expansion, into left hand side, and right hand side is this q of x times psi. So then what you and plug compare with each factor. Okay. So that's what you do. Okay. So yeah, time psi. Okay, maybe time psi is better. For time psi. Okay. So therefore one can compare between these two, right? So the first thing one will notice that here, so the 1 over h to the 0th order. Let's look at 0th order. So then 0th order is that the h square here cancel 1 over h square here. Okay? And what's left is the n equal to 0 part, right? Left hand side. That's the only contribution you will get. Okay, so therefore you get the S0 prime square. And right hand side is just q of x. Okay? It's just q of x. Is that okay? It's a q of x. That's what you get. Okay, so that's the, and second order, second order is also, you can do it. This is the h, no second order. First order is something like this one. 2 times S0 prime, S1 prime, plus S0 double prime is equal to 0. Okay. So that's what you get from this expansion. And so on. So that's what you get from here. So therefore, the leading order of the the solution of this equation at the leading order is S0 of x is equal to x square root q of x dt dx dx. So that's the leading order behavior of this wave function S0. Okay, so that's the leading order. That's why you get the here's how to say square root q of dx in the leading order. Okay, and then S1 is in fact, if you solve this equation, S1 is equal to something like that, 1 over 4 log of q of x plus constant. Okay, plus constant. So therefore, you plug this one into here, and then this prefactor will show up. This prefactor is short. So therefore, this part is in fact the leading order is S0 of x, and this part is coming from S1 of x. Okay. And so that's what you get from WKB. So now, what kind of variable we would take for H bar? So to do that, we will do that here. Now we will use the expansion of Q of x. So we assume that here B max is very close to, so B max is very close to omega, so that the Q of x can be written like this way: Q0 plus 1/2 Q0 double prime x minus x0 square, and then plus order x minus x0. X0 cube. So here I just assume so. Instead of R0, I now use the X0 here. And then Q of X is, of course, is something like, I already erased, most likely B minus omega squared. I think it should be omega squared instead of omega. Yeah, sorry, this is omega squared. B plus minus this. And the Q0 is the value at the X0 of this one. The value of the X0. And just under this assumption, we can just write down that this whatever Rachel Wheeler or the Rayleigh equation can be written as follows: B squared psi d t squared plus minus I Q0 double prime minus 1/4 t squared plus psi like this way, where the t is in fact equal to t is something like some factor times x minus x0. This part is not so important. I mean, it's just some constant in x minus x0. So here, so that x minus x0 is a variable in this region, and then with some constant, and just write down like this, and then solve the we solve this equation. Before solving this, we just write down this guy is equal to nu plus 1/2. So we just write down this part factor is nu plus 1/2. And so this equation is called something like I don't know. It's called some relative Hermitian polynomial. So one can just solve this exactly. Some special function. It's called parabolic cylinder function. So this solution, this equation has a solution. So this has a solution. This has a solution. So which is called d nu. It's often denoted as d nu of t. Like this one, d nu of t. And then, so in region 2, so this is region 2. So this matching region 2, so the wave function is behave like as follows. Psi is equal to some function a d nu of z and plus b d minus nu minus 1 I z, where z is equal to this number minus r star bar. I just rewrite this x and x minus x naught in terms of r star here. So this is a wave function, and then so using a simple behavior ongoing wave function. So using a simple behavior. So this is some special function. It's called parabolic cylindrical function. And if you use this region 2, and if you use the asymptotic behavior of this function, one can show that the psi region 1, no, region 3. Region 3, when r goes to infinity, r also goes to infinity, one can show that the a is equal to e to the I pi nu d nu e to the minus d square over 4 plus minus square root 2 pi some constant and the gamma function inverse. Anyway, so it's a kind of complicated function, but you have some oscillation mode over 4 z minus nu minus 1 e to the z square over 4. So that's the case. Anyway, it's too late. And then so here sorry, this is 1. Sorry, this region 1. Sorry, this is 1. This is 1. This is 1. Region 1. I already read it. Sorry, I'm very sorry. So my assumption is something like this one, and then here we take the omega square is around here, omega square, and the region here, I call it this one is region 2, region 1, and region 3. And then here the behavior of the asymptotic region r goes to minus infinity. Sorry, minus infinity is like this. And it turns out that we assume that this is around the the horizon. It should be ingoing. So we have to take only ingoing solution, which is this guy. This is ingoing. This is ingoing. And this is outgoing. This is outgoing. This is outgoing. So therefore, this function should vanish. So outgoing should vanish to satisfy boundary condition. To satisfy this boundary condition, we have to impose the following condition. So this minus nu inverse should be 0. So this means that the nu has to be, so this gamma function has to vanish, which means that one of the gamma function should vanish, which means nu should be positive, non-negative integer. Is 0, 1, 2, 3, all the integer. So this is that. This will give you the discreteness. This will give you discreteness. Okay. So therefore, so recalling that this nu is something like coming from Q0 over some. It's defined by some Q0. So this means that the Q0 over square root Q0 double prime is equal to I n plus 1/2. Like this way. So therefore, to satisfy a boundary condition by using this WKB. So WKB, I use it that here is the B max is very small, close to the omega square, and we just use this expansion. What was it? The expansion of this potential. Okay, expansion of this potential, and solve the this differential equation. And that will give you discreteness of the spectrum. And then this one actually you can check the numerically. Numerically, it's kind of a very good approximation. I will show you later. I think that's all I wanted to explain on the blackboard. Yeah. Today, let me think. Yeah. And then let me show you what's going to happen. So let me erase. So as I mentioned, this ring down phenomena is that so here, as I mentioned, ring down phenomena can be seen in a gravitational wave, which, I mean, if you look at the LIGO's, website or whatever, the first one is always you found this kind of like a behavior. Like, I don't know. I mean, I just rough form of like this. So here, the black hole, there is a binary black hole. It's rotating each other. And this rotational frequency is really, this gravity will give you rotational frequency here. And then, around here, black hole will match. Around here, black hole is, just the distance between them becomes smaller and smaller. Okay, like this one. So the alpha frequency become shorter, like higher. And at the end, around here, there's a black hole will merge, like this way. Okay, black hole merge. Okay, and then whatever, it's rotate, and around here, so it become try to be stabilized. Try to stabilize. Still not like a round shape, maybe like this way. I don't know. Just a little bit you have to perturb, like this way, and then eventually it becomes the curved black hole. Whatever, curved black hole. There's an algosphere, if you want to be precise, become curve, stable curve, like this. And around here, so this damped shape, so this is called, damped shape is called ring down phenomena. Ring down phenomena. And then here, if you look at this spectrum of wave function, it behaves like this way. So wave function, if we just this log of psi, and then log of psi, like this way, and then here is time. And after the black hole merger, it behaves like this way. So it's just a monotonically decreasing, and then, but there's, as I mentioned, so there's some oscillation occur. So is some like this way. So this part is quasi-normal mode. And after that, it becomes like a power law in time. So last time is power law in time. Some t to some power, negative power. Then actually minus 2L plus 1, something like that. 2L plus 1, something like that. And then here it's just the slope of this one is omega, imaginary part of the frequency inverse. like this way. So the slope of this how to say? Decay is the imaginary part of this quasi-normal mode. As you recall, this is r plot plus I and I plot. Slope will give you like this. So this is the typical phenomenon of the gravitational wave, and this one is already observed in LIGO. This phenomenon. Okay. So that's what's really happening in the black hole. Okay, I think it's a bit early, but let's take a 10 minutes break, and then I will move on to the slides talk after that. If you have, yeah. So let's take a 10 minutes break. I will prepare the slides and so on.
If we consider a graph GW emitted from infinity to the black hole, why the perturbation GW tends throughout the potential wall?
But it's not infinity, right? It's
Perturbation metric
from infinity, phi infinity.
Yes, from infinity to the black hole. Why can this perturbation metric cancel out the potential wall?
No, here. So infinite at the infinity, we only assumed it's outgoing. So there's no perturbation ingoing phenomenon. So perturbation occurs in somewhere in the middle.
The outgoing mode is just a reaction of the
Yes.
about the black
Perturbation.
hole.
Yeah.
But you mean perturbation?
Yeah, perturbation
Right.
occurs somewhere in the middle. That's my assumption. So that at the infinity, it's just only outgoing. So it's just a reaction of the perturbation. So then here, perturbation occurs somewhere in the middle. That just
You mean the perturbation is just a deformation of the horizon of black hole?
yeah, the metric. Yeah. Okay, give me. I forgot to bring this one, so I need to. Okay. So we have a 10 minutes break, so I will. Oh, you have? Oh, good, wonderful.
I take it. You can try it.
Good, wonderful. Oh, somehow it works. Okay, good. It's now. Okay, I think. Wait. I don't know what's going on. This one is this one. This one relatively okay. Good. And then where was it slided last time? Reference. Oh yeah, this guy. And then also, oh my goodness, I forgot the, let's see, I forgot to download this one. Just a moment, let me check the, oh this one, oh yeah. What's going on? Oh yeah, this one. No,
You cannot work.
no, it works. It works. No, I just want to. Oh yeah, it should work. Yeah, it should work. Presentation. Oh yeah, presentation. I think this is the one. Okay, good. Oh, somehow it just, I don't know why. Okay, maybe something strange here. How about the full screen? Okay, maybe. PDF, single page contents. Okay, that's maybe better way of looking at. Okay, that's also okay. My internet working or not? Okay, it's working. Okay, good. Okay, then maybe. Okay, shall we resume? Okay, I'll be brief. So I wrote this perturbation of black holes in the last section. Let's see. And then the derivation of this Recce-Wheeler equation, maybe I should use the single page mode. I think, what was it? PDF single page continuous. Okay, so the derivation of the Recce-Wheeler is the written here. Last time I didn't, so this is spherical decomposition. I will explain how it happens later. So this for axial case, these are the decomposition. I think it's big enough, right? Okay. And for this is time space part. This is the second line time space part, and third line space part. And then these are the tensor spherical harmonics that I will briefly recap later. And from here to Recce equation here, Recce equation, you have to take some gauge which epsilon 2 E2 is 0, and then also we assume m equal to 0. M equal to 0 case, all the derivative of phi will vanish. This part is vanished. This part will vanish, and this one is also do not contribute. And then at the end of the day, so what you get is this very simple factor for metric. So that's the what you get if you assume the H2 goes to 0, and so the spherical harmonics m part is 0. So then one can just write down the metric like this way. Then it's easy to write down the Einstein equation. That is this one. And then also so Chandrasekhar's way is written here. So that's I tried to write the blackboard, but now it's written here. So I think you can just go through by yourself instead of writing this equation. I think it's more illuminating to just write down the perturbation Schwarz metric like this way. And then you just write down the Einstein equation in this form, and then just do the manipulation to get this Recce-Wheeler equation. Sorry, Recce-Wheeler equation. So that's the case. And then I wrote a reference in here. So this sorry. So what's going on? So here, these are the standard reference. I wrote reference for this black hole perturbation theory. Of course, the first one is I don't know what's going on. So the first one is Chandrasekhar's book, and the other is more recent one. And then I find this the Bertie's lecture at the ICTS is fascinating. So if you just look at this, click this Bertie. And this Bertie, if you click this URL, you can go to this website. And there is this Bertie's, he's world expert on this black perturbation theory. And lecture note on the other sources. Actually, there is also videos there in the YouTube. I think 5 version of the YouTube, so you can take a look. But if you click this one, it'll go to the Dropbox folder. Of course, so you guys have a VPN, so you can just have access to Dropbox. And there's a lot of files, so you can just download it. And there is some lecture note, which is, so these are file, and then there's a lecture note. Which is wonderful. I guess which is wonderful. I think it's a big note, even though it's It's just 100 pages. So, I mean, to explain all the how to say black hole perturbation, you need to have like many lectures. So I just to be briefly. So the spherical harmonic decomposition for tensor and so on are written here. So those are the spherical decomposition. This is polar spherical harmonics is written here like this. These are modes for each mode is satisfies some differential equation. And this is the axial one. That's what I showed last in my lecture note. And here we assume this phi derivative will vanish, and this phi derivative vanish. And by gauge, I ignore this d part to get the Regge-Wheeler equation and so on. So those are all the spherical harmonics. It's a really complicated one. It's all everything written here, and in particular, they include a mathematical file. So in this note, they mention this as shown in notebook or whatever, Gerlacha Sengupta. So if you just open this file and go to Mathematica, and then corresponding files one can find like this way. Do I have? Can I? Oh yeah. So this is the spherical harmonics. One can just open it, and then, oh, you cannot see somehow. What's going on here? What's going on? Sorry. Like, then you can see that. So here it's the spherical harmonics, the way you decompose region and then so on into the spherical harmonics written coded, and these are the really decomposition of into the spherical harmonics and so on. So everything written here in Mathematica beautifully, so you can play around and so on. So it's very nice. The part I talk about WKB today is also from this note, actually, indeed. So if you go to WKB here, that's the part I showed today. WKB is written in this, the one I showed today is this part. And then if you solve this equation, you can get that this function D, and in the region 2, so it's written in linear combination like this way. And if you go to the region 1, near horizon, you have to throw away this outgoing mode instead to have an only ingoing mode, so that this factor should vanish, so that the gamma function requires that the nu has to be some non-negative integer. Okay. So to get that will give you some Bohr-Sommerfeld quantization rule. I hope you guys can see that. Okay, so that's the case. Okay. Fine. So that so I highly recommend to visit this website, and also there's a YouTube of the lecture, 5 lectures of all these courses. If you search in YouTube, you can find his lecture. So, okay. Anyway, so those also are very, 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 very useful, and this lecture notes are very well written. So that how do you do the spherical harmonics and so on? It's super complicated, but one can, if you read this, if you read this, one can just solve this, and using Mathematica, one can solve and so on. Yeah, I mean, even scalar field, I mean, it just, it's written, so this is the wave equation for scalar field, and they do the spherical decomposition in here, in this part. PLM is essentially the PLM, and also e to the im phi is the YLM, essentially. And then just assuming this phi, admit this spherical decomposition, one can just write down the Klein-Gordon equation in this way. and the potential is written here. Okay, potential written here. And to derive this equation, if you look at the YouTube of his lecture, he derived this equation by on a blackboard, and it took half an hour. And it's a huge computation, and he mentioned that if you even scalar field takes 30 minutes, vector and tensor would take like a whole lecture to derive this Ricci and Wheeler equation. So he omitted, and just instead he just added this lecture note and Mathematica. So that's the case. So I will follow. So you guys can take a look at this lecture note if you're more interested in the black hole perturbation theory. Okay, another useful source I found is this guy. So Leo Barak. The slides is very useful, and then I will just open. I think so. This slide is also very useful. First, they talk about Newman Penrose and so on. But if you go to this method of perturbation theory, I don't remember how well. Okay, so this is the case. So he also talk about how do you do the, this is Steve Penrose. Okay. So black hole perturbation theory, and then here he also talk about the spherical harmonics of scalar and vector field. So this is exactly what we saw just now. YLM is the, so here this guy is the spherical harmonics expansion of the scalar field. But if you go to vector, you need to introduce some other how to say, basis. So which is some derivative of the spherical harmonics here. I hope spherical harmonics here. And you have to expand it in terms of spherical harmonics. For tensor, it's much more complicated. So the one I show is that the even involves some derivative of spherical harmonics. Those are the tensor spherical harmonics. And he explained how you do the expansion of the spherical, the perturb metric in terms of spherical harmonics here. Okay. And then just solve the Einstein equation. They just did some assumption and so on, and then they solved the what was that? Yeah, equation for perturbed solution by assuming some gauges like this in spherical harmonics. Okay, and the psi in the Ricci Wheeler Zerilli is in terms of this mode of the metric. So D and A and D and A are some modes of the metric, perturbed metric, and it's a combination will give you this psi lam, which satisfy this Ricci Wheeler Zerilli equation like this way. So that if it is vacuum, this right hand side is 0, but if you assume that some matter is there, so you can just have non-trivial stress energy tensor. And this is a form of Ricci Wheeler effective potential. Okay, and then so here. So we can just solve the perturbation theory and so on. And in the car case, this perturbed equation is much more complicated. So this is called Tucholsky equation. This is in the car case. That's why I wanted to avoid. So I just use slides to show. So this is a curve version of Ricci Wheeler equation. Okay, Ricci Wheeler or Zerilli equation. And this Tucholsky master equation can be just decomposed somehow. This phi s can be somehow have a decomposed factorization property. So this R and S, which is S is something called orthogonal function called spin-weighted spherical harmonics and so on. And one can look at the R part of the equation become relatively simple like this way. And one can solve the numerically and so on. So those are the car case and car case. So that's why I just wanted to show this via slides. Okay, so the rest of the slides, it's go beyond my expertise. I'm not going to go into the detail. Okay. So this slide is also very useful. I will send you via WeChat later. So I highly recommend to take a look at it. Especially this Bertie's one is wonderful. Another thing, and before, what was it? Yeah. So let's recall some history. What was it? I think, is this the one? Yeah. So the history of this perturbation theory is written here. It's also a good idea to look at how this development occurs for black hole perturbation. It's too much. Maybe you can take a look. Or is there any way to, I don't know what's going on. Anyway, let's not do something weird. Okay. So it's written 1957. So Lech and Wheeler found the perturbation of the Schwarzschild geometry. Okay, so this is the beginning of black hole perturbation. Newman Penrose used some method to formulate some method to gravitational radiation in terms of spin parable. 1963, Kerr found the Kerr black hole solution, and then 1967, Wheeler coined the term black hole. So before around this time, they call it the black hole, the object black hole. And so as you know, around this time, so the Hawking and also Penrose singularity theorem appear, and then also uniqueness theorem, Israel and so on starts in 1970. So these how to say, late 1960s and then beginning of 1970s go golden age of general relativity, and then Indian physicist Vishveshvara found the ring down phenomenon. So this is the ring down waves. So it's a wave. It has a complex value of this. So damping phenomena occurs. So that's the 1970s. And then also Zeridi found the even version or polar version of the perturbation theory, perturbation solution. Okay, and then 1973, Tchaikovsky applied this Newman-Penrose formalism to Kerr geometry to get this Tchaikovsky solution. So that's the 1973. I went too much. And then 1975, Chandrasekhar and Dettoveiler compute numerically the frequency of this quasi-normal mode. And they show that the Lech, Wheeler, and Zeridi have the same spectrum. So that's the same quasi-normal mode they have. So that's the isospectral. Okay, and so on. There's lots of things going on. In 1983, this famous book by Chandrasekhar monograph appeared. This is mathematical theory of black hole. I mean, you guys already took a look. I mean, you can just look at the this book. I mean, it's 500 pages now. No, 600 pages. It's a full of equation. It's an amazing book. I don't know. I mean, it's kind of amazing. It's 1983. It's not so much computational. How to say? Tools are not available, but it seems like he can perform lots of this kind of complicated equation by himself. It's quite amazing. Chandrasekhar is an amazing guy. I personally think even in my research, I did lots of calculation, but using like a mathematics and so on. But this is way harder. Yeah, so it's it's an amazing book by Chandrasekhar. It's appeared in 1983. Okay, so that's a milestone of in this field, and then there are many how to say development. I'm not gonna go into the detail, but yeah. So the 1985 Schutz and Wohl developed WKB approach to the black hole quasi-normal mode and so on. There are many things happen in later times, even in recent times. Yeah, so for instance, Creighton described a search technique in ring-down wave function in LIGO, which is now used in the detector and so on. Many things happen. Anyway, so if you take, so this paper is also cited in my lecture notes, so you can take a look. Yes, those are the history of the black hole perturbation theory. Just and this one is all how to say numerical WKB approximation and so on. But recently there is some technique is called what was that? Even string theory has give you some technique to solve the quasi-normal mode. So this is a paper. The previous review is the title is like this way. This one is also very nice review. So, sorry, topical review quasi-normal modes of black hole and black brains. So as you see, this Emmanuel Berti is one of the authors. He's a leading expert of this field. So I highly recommend. Also this one too. It's a detour, but there is some method analytically applied. This analytic method can be applied to this quasi-normal mode, even from string theory and so on. There is a paper by Aminov, Grassi, Hatsuda. There is some Bose-Sommerfeld quantization method has been used in superstring quantum field theory. And then superstring quantum field theory method can be applied to this quasi-normal mode. Because I mean, the equation that appears in superstring gauge theory is exactly the same as this Lecce-Wheeler. This Lecce-Wheeler and then Zerilli type equation that appear in superstring gauge theory. And if you use technique of superstring gauge theory, one can solve this quasi-normal mode like this way analytically. And if you compare numerical method, it's very, very close to each other. Okay, so those are method this paper is 2020. So there are lots of methods one can now apply to this quasi-normal mode and so on. Okay, and then this is kind of like a Tukhowsky equation. Even you can apply for Kerr case or this method, and then one can get some numerical solution for analytical solution for this quasi-normal mode for even Tukhowsky equation. So those are recent development. we found. Okay, so that's all what I wanted to show today. Yeah, I think that's all I wanted to say today. Yeah, so then I think yeah, so today's the last lecture, but it's okay to finish like 1 hour earlier, I guess. I mean, yeah, thanks for taking my course, and then maybe we'll see you summer. Yeah. Okay, anyway, so let's finish the course. I will send you this file to you via WeChat.
What about the final test?
No, I don't care final exam. So a grade will be determined by grade homework sets. I mean, yeah. It's a. Do you want to do the final exam? No, right? No, right? Of course, no, right?